public access that must be disabled, TLS must be enforced, HTTP must be enforced, shared access signature or those tokens should be minimized. Whenever you generate such token, you must also put there and the appropriate permissions and the appropriate IP. And normally, you must do VNet integration. It means those resources that we previously saw, they will have the appropriate subnet, and just that subnet need to have access in your storage account. Despite this subnetting or service endpoint, always it's recommended to be with private endpoint. It means private endpoint, whichever resource will be somewhere, we can create like a private IP in any VNet that we want. And with that, it goes totally private, the appropriate resource, which is here the same and for the storage account. Again, important, very used resource for all developers is the storage account. The next topic, which you probably mostly have visited, is the Azure Sql. In Azure, there are like 3 options for using SQL. The older version is by having a virtual machine with installed SQL, which is not recommended. The other version is to use Azure SQL database and SQL server, which is like a PaaS. And there is a SQL managed instance, which is again like a PaaS. But there are some differences between managed instance and between a single. Managed instance, it's mostly like the on-premise SQL. It has features like sending emails. It has features like a cross-database communication, like queries cross-database. And it has like full VNet integration. But for new applications, it's recommended to use Azure single, let's say, Azure SQL database, which is more PaaS. It's not originally like the on-premise SQL, but Microsoft manages more, Microsoft optimizes, does recommendation, and then also we can group multiple such servers in Elastic Pool for more cost efficient. In Elastic Pool, we will put, if we have like a different time zones or in different times to be used those loads, then we can be more cost efficient by using the Elastic Pool. For SQL, whichever SQL you will use, you must use auditing, you must enable the transparent data encryption, you must enable the Azure Defender. These are some must rules that in production must be there. Azure will force you to use them, but also if you use PHI data or something, you will have auditing or HIPAA high trust standards. You must do, let's say, these changes on your resources. Another resource is the Postgres Sql, which it starts to be heavily used. It is cheaper than SQL, and very important, now there are 2 versions of Postgres. It's like a single server and a flexible server. Microsoft now forces to use a flexible server. Even some features are missing, like private endpoints and some other. Still, they force using the flexible server. When using a pSQL, Postgres, we must again enforce to be in the VNet. We must enforce the TLS. We can enable Azure Active Directory administrators, or we can enable Azure Active Directory logins. It means to not create static users. The existing Azure AD users can get a token, and with that token, let's say, sign in Azure AD, and with that, we will have a control who has been there. Again, recommendation is to use the Azure Postgres flexible server. Like two big drawbacks. It doesn't have a private endpoints, and it doesn't have a support for Azure AD authentication. The next, and let's say important topic for databases in Azure, it exists from May 2017, is the Cosmos DB. Cosmos DB, it's like a storage, like a database, which can be one of 5 types. Can be like SQL, which is no core database, it's a JSON database. Can be, despite a SQL, can be MongoDB. It means if you have a MongoDB, you must use Cosmos DB. It can be Table API, Gremlin, or Apache Cassandra. Recommended by Microsoft, if you create a new Cosmos DB, is to have like a SQL. It's called SQL API. Again, it's a JSON database. This should be used if you have application that will be used throughout the world, because just with some clicks, you can create a copies of this NoSQL database around the world, which copies can be read-write, and can be used for applications which will have like millions of users all around the world, all for backend mobile APIs, because it will be all around the world. Whenever you want, you click, can be a read-write, let's say, copies of the database. It has a concept of partitioning, which is very important topic there, but we will not go there. Again, if you need your database to be in multiple places all around the world, this is the solution. That is optional thing to enable in multiple regions, but if you have like on-premise MongoDB, you need to migrate there. Again, you have this option in Cosmos DB just to migrate there. Regarding the synchronization, how fast will happen if you save something in Europe and how fast will be processed, let's say, in USA. For that, we can do by setting up the for developers is the Redis cache. Because the database access can take time, those data you can put in Redis cache. This is implementation of Apache Redis implemented here in Azure. And as such, it's very easy for you developers. Just connection string, get set keys, you can put there for how time will be, and automatically it is more faster getting data from Redis than from a database. As such, different tiers have different number of connections and different, let's say, size that can save there. Despite that, even it is cache, it has in it like a databases. Like a premium cache has around 20 databases, and it happens for special purposes. Developers want like to have some data in one database, other data in another database to be and more optimized. Here the trick is just with key value, and within the key we can do some hierarchy, like write some name, call another name, and then we can have some type of the hierarchy. We had such situation in Maersk, the Danish company for containers, where for Cosmos we paid too much money, and then we did optimization for less money just by saving data here in the Redis cache. Another very trendy resource is the Azure Container Registry. Probably you have used the Docker Hub. This is like a Docker Hub, private Docker Hub for our applications, where we can create, persist, save, and let's say scan our images. It means instead of installing Docker on your computer, you can just send your Docker file to Azure Container Registry. It will build the image and save the image in the container registry. Save the image in the container registry. As such, it has another feature that you can buy one container registry. It has option for replication. You can replicate your data images in USA and whenever you want, and then you can reuse that for high availability. The biggest feature is in the build, which I mentioned. We don't need to spend resources for building. We just give to container registry the Docker file. It will build, persist there the data, the images. After having the images, we have 2-3 options for deploying those images. For dev and test purposes, again, just for dev and test purposes, is the Azure Container Instance. Azure Container Instance is very fast resource. Within a minute, our container image will be up. We'll have its public IP and let's say custom domain, but it cannot have a SSL certificate. Again, that's why I said for dev and test, cheap resource. You will have your resources, do tests there. By default, it supports one container image to deploy. If your application will have multiple images, then you need to use container group, which has like 2 options for deploying that with YAML or with ARM. And again, the most used at the moment, and I can say in the future here, is the Azure Kubernetes service. You probably use the Kubernetes for independently on which, let's say, cloud provider or where. Azure Kubernetes service is managed by Microsoft. We don't pay for the master node. It's managed, upgraded by Microsoft. We pay just for the nodes. The nodes are just the VMs which Microsoft manages. We can have a Windows, Linux nodes, and there we can host our, let's say, containerized applications. As such, in this AKS, normally We should enable RBAC, Azure AD RBAC, like to have in a level of namespace to have a different authentication authorization. Then all the keys secrets must be saved in a key vault, and then enabling CSI driver, we can connect the key vault with our AKS. Despite that, we should also restrict access to API of this AKS by using IP authorization or by using just private AKS to not be available from outside, which is a very big constraint in big companies. Also, for the, by default, pod with pod can communicate, which is not good. That's why we need to enable their network policies to separate communication between pods. We can enable and mesh and Istio, but that's more advanced topic. We should enable the defender for Kubernetes. It should have a backend private connection to the container registry and exposing these applications again through a web application firewall, which can be application gateway or Azure front door. Container images will be scanned in the container registry by using their Azure Defender. Again, this is the reality, but for the next few years, this is very interesting resource, very used resource, which is just growing and growing. And this AKS has like automatic scaling and has other features which make the life as developer or DevOps easier. And the last resource here, which for developers maybe can be the most favorite, is the application insight. Application insight can be enabled like codeless or through code, and then in the application insight you will have in the portal like live view of your application, of your web application. You can see the number of visits, you can see per transactions what requests come, what is sent to them. You can see like a map of your applications. You use different resources, it will draw a map. You can create availability tests. It will ping your site every some minutes. Despite that, here you can create availability test that will check the SSL certificate expiration. It means automatically will notify you 30 days or more before the SSL certificate will expire. We don't pay for application insight. You will pay just for the logs in the log analytics. It's very powerful for debugging, and it's like a must for developers. I hope I was quick. I wanted to point just the most important topic, and for this session, I hope you had any previous knowledge, let's say, for Azure. Any question, please? Any question regarding the topics that I presented? Yes? Correct, yes. Correct. In one Azure Service Bus namespace, that is called Azure Service Bus namespace, we can have a multiple queues and a multiple topics. It's like a namespace, then multiple. Any other question, please?
And I think
correct. Regarding the maximum connection, yes? Correct, correct. Yes, regarding the flexible, regarding the Postgres Sql, like a single and flexible. In the single one, we have a smaller number of connections we cannot configure. In the flexible, we have up to 5,000. We can configure then how much we want to be. Another topic for the storage. It has a lag that you will start with storage, let's say 2 gigabytes. Then you cannot go back. You can just double that, like from 2 to 4 to 8 to 16. Another problem that the colleague mentioned is the same in SQL and also in Postgres, that when you will reach 100% of your storage, the database will not work. To overcome that issue, you must create alerts to be notified and to manually, in this time, let's say, double the size, otherwise it will stop working. Correct. Correct. Correct, and also in flexible server there is an option for a maintenance. You can define where it will be maintained by Microsoft. You can set that one just on Sunday. And also the flexible server has the option start-stop. You can start to pay less money, which in single server you don't have. Again, the usage of Postgres Sql is on rise. Any other question, please? Thanks. It was my pleasure. Maybe I spoke somehow faster, but because of the time limitation, I had to do that. Thank you.
Okay. Thanks, Visnik, for your insight onto Azure and the world of it and the best practices. Now to our second speaker, Roman Hoog-Anting. Was it correct? He will present us Go, the new kid on the block of compiled programming language. It is used more and more by companies, and even companies that have, other companies are right now replacing core components which were created with older and well-established languages. So right now it's taking off. In this talk, we will look at different kinds of algorithms and practically how to transform them into concurrent code. So let's give a warm welcome to Roman.
Thank you. Yeah, my name is Roman. I'm training engineers and students in software development and system engineering. And thank you for being here. Today we are going to look into how to write software in a way that it might use more than one CPU core at a time. So who has used Go before in the audience? Please raise your hands. Okay, keep your hand up if that code used Go routines. Few hands up there, thank you. All right, this is our roadmap today, and we will be looking into two concrete examples, do some theory first, look at the concept, how to transform an existing algorithm into a concurrent implementation. This always adds complexity, of course, but we try to keep it simple today. And in between, I will talk a little bit about Go routines. Let's have first a look, sit back, take a deep breath and look at the hardware side of things. First, you need more than one CPU core, but nowadays this is just taken for granted. Come on. I ordered some more CPU cores here. And of course, computers are faking it a little bit. You can run as many applications at the same time as you like, and by switching very fastly between different processes, they will make the impression that this device can run as many applications as you like at the same time, but in reality, only a few will have a chance to actually run. On the software side, we start with a classic, very simple algorithm. You have some initialization going on at the beginning. Then you need to compute something, do some processing, burn some CPU cycles for a good purpose. Go to the next item, creating a loop. And after you processed all the items, you have something to show for and output the result. Now, how can we do this using more than one execution thread at a time? Of course, you have to implement your program in a different way. It won't come for free. So somehow we try to split these tasks into groups, run them on different threads so they can be distributed across CPU cores and complete in shorter time. In our first example, I will use something easy, something which is very willing to be distributed across different CPU cores. We are going to ping many hosts and try to complete as fast as possible. But let's start simple. Go already encourages you to implement something in a very simple way and only optimize after the fact, after you become aware that something needs to be improved, and then you can have a close look what to improve. Now, for this sequential algorithm, question is how long does it take to complete these pings? And to keep it simple at the beginning, we will do everything sequentially. We send a ping to one host, wait for a response for a given amount of time, not forever, of course. And then when we are happy with the results and we made a conclusion, we go to the next one. The time this is going to take to complete is obviously the number of hosts multiplied by the timeout you are going to apply for each single host. I use this example in interviews a lot, and over time I received very interesting suggestions how to improve this algorithm. Let's have a look. So some people would say, reduce the number of hosts. Who in the audience would take that approach? Anyone there? No, I see head shaking. Of course, at the end of the day, you are not done when you choose that approach and you miss some of the information you're supposed to collect. Next one would be reduce the timeout. Become impatient. Don't wait so long. But how long should you wait in the vast internet to gain accurate information? So here you are done at the end of the day, but you lose accuracy in your result. You are not waiting enough for some busy hosts until they respond. And then, of course, you could break up the sequence of this algorithm, by pinging all of these hosts at once or very quickly, and then begin to sit and wait for the responses to come back. But for my example, I don't like this. I don't like to change the algorithm. I want you to show you the simplest amount of changes that will lead to concurrent code. So today, we are going for the Go routines. We are going to split this code up in order to run on multiple threads on Go routines. And to do this, we need some organizing in the beginning, firing up these Go routines. Every Go routine will deal with only one host. We try to keep it simple, remember. This is a different representation of the same algorithm. It's just emphasizing on two phases. There is the fan-out phase, distributing the tasks, and then there's the collection phase. In a consistent way, collect the outcomes of every single host and keep counters up to date. Now let's see how this is done on the console. I will start with the single-threaded, very simple implementation that I explained in the beginning. We will create variables to hold the results, and of course, we have to return them eventually. And then we need some simple kind of a loop to process all the hosts, not forget one single one, and this will happen in sequence. No complication here. First, we send the ping and wait. This is all done in this one function for the result, and afterwards it returns and we can check the Boolean outcome, whether that host responded or not in due time. We will keep track of the results accordingly in these two variables and keep them updated. And this is our algorithm. I prepared a couple of unit tests to make sure after the implementation, hey, do they turn green or not? And not all of them are happy. The reason is one of the unit tests was designed specifically to check the overall execution time of this simple algorithm, and of course it detects that at the end of the day we are not done because this takes too long. Okay, so how can we transform this into a concurrent implementation? We have to somehow make that decision to fire up new Go routines and put the specific part of this existing algorithm into a new Go routine. Of course, we will choose line number 24 here because this is the workhorse. This is where the action happens. We will create an anonymous function to keep the code readable and short, and we will include the execution of the ping in that new Go routine, and also the collection of the results, but we will use a channel instead of a variable, otherwise concurrency opens a whole can of worms